Hi, I am Ravi and I welcome you to the video tutorial on Introduction to Machine Learning. We will start by looking at what is machine learning, how machine learning works, and finally we will look at the different evaluation techniques that are available to us in machine learning. So let's get started. We have lots of data generated every hour than ever before. So, machine learning in very simple terms is nothing but extracting knowledge from those data stores using an algorithm so that we could make better predictions about our future. And broadly, there are two kinds of machine learning problems: the supervised machine learning and the unsupervised machine learning problem. In this video, we will discuss about supervised machine learning. In supervised learning, both the input and the desired output are provided, and our model tries to learn the relationship between the two. Let's understand how machine learning works with a simple example. One of the classic supervised machine learning problem is email classification, that is, to classify whether an incoming mail is a ham or a spam. Suppose we have a dataset that contains historical data about emails. Each record in the dataset is an observation, and each column in the dataset is a feature. The features for email classification could be the length of the email, or the presence of a certain hyperlink, or the presence of some words that are very common in spam emails. This is the input to the machine learning algorithm and is called the feature matrix X. In supervised machine learning, you also have the labels, which is the output of the machine learning algorithm, as it predicts whether an email is a ham or a spam based on the input features. This output is called the response vector Y. So once you have this labeled dataset, you can choose any algorithm, for example a KNN or a logistic regression or a random classifier, to train the algorithm with its training data. The model looks at the input data and learns the parameters or weights of the input features that would accurately predict the output response. Or, in other words, it tries to find the relationship between the input features and the output response. Then, it tries to construct a model, or you can think of like an equation where it can predict the output response as a collection of input features. So, when I say the model learns the parameters, it learns the different weights of the features that need to be used to predict the response. And based upon the value of R or the response, the model will conclude if a particular email is a ham or a spam. Note that some features have a very positive correlation to the response. For example, I am almost certain that if there is an image embedded in an email, it is most probably a spam. So this feature gets a weight close to 1. And some features have negative or even no correlation to the response, and their weights will be determined accordingly from the training dataset. As I said, you can run different algorithms on your training data to produce different models, or one algorithm itself may produce different models, each with different parameters. So, our goal is to choose a model that predicts the response for the unknown data with the highest accuracy rate. So, how do we know which model predicts the best if we do not know the true response values for the future dataset? To select the right model for the problem, you need to evaluate the model first. So, you need to understand different evaluation techniques in machine learning. But before looking at the evaluation techniques, let's talk about the dataset that we will use. Let's first look at the iris dataset that we will be working with in this video. It is a very popular dataset provided with scikit-learn that predicts the species based on the length and width of sepals and petals. So let me go to Jupyter and import the dataset. The iris dataset is provided in sklearn,
So let me import load underscore iris function from datasets module and save the iris dataset in the variable iris. If you write iris.feature underscore names, you will get the feature matrix. To see the response values, just enter iris.targetNames. So this is a classification problem because you are predicting if each observation is a setosa or a versicolor or a Virginia using the dimensions of the species. So let's extract the feature matrix and store in variable x and store the response vector in variable y. Let's check the shape of the X matrix. There are 150 different observations in this dataset and it has 4 different features. And Y contains 150 response values. Now that we understood what is within our dataset, let us go to slides to look at the different options to evaluate a classification model. There are several tools to evaluate a classification model. They are training and testing the model on same data, or using train test split, or even more advanced is using k-fold cross-validation. Let's understand each of these with an example. Let's look at training and testing the model on same data. Here, we train our model on the entire dataset and then we test our model on the entire dataset. This is a very basic method to check if the predictions by our algorithm is correct. By testing our model on the dataset for which you do know the true response values, you can check how well the model is doing by comparing the predicted response values with the true response values. So, one of the ways to evaluate a machine learning model is to train the model and test the model on the entire dataset and evaluate how well we did by comparing the predicted response values with the true response values. First, let me import a random forest classifier from sklearn.ensemble. Random forest classifier is a machine learning algorithm known to be one of the best performing machine learning models. So what I will do is first I will use that algorithm to classify my species, and before that any process of training the model and predicting the outcome is a 4-step process. So the 4 steps are, the first step is the importing the class, which we have already done. So we have imported random forest classifier from sklearn.ensemble. The second step is to instantiate the model with a default set of parameters, which we will do now. And the third step is to fit the model with the data that we have. And the fourth step is to predict the model for the response values. So now let me instantiate the model. So here I will use a variable called CLF. You can use any variable, that really does not matter. And I'm gonna say random forest classifier in brackets. So which basically means that particular algorithm is getting instantiated and I am assigning that to the variable called CLF. The next step is to go and fit the model. So I will use the variable CLF and use the fit method on that random forest classifier to fit X and Y. Here just recall that X is our feature matrix and Y are the response values, or X is our input to the algorithm and Y is my output of the algorithm. I am getting an error saying that X is not defined. That's basically because I am restarting the notebook and much of the cells above my sklearn.ensemble have not got executed. So what I will do is I will go to cell and I will run all the cells now. And now it should get executed successfully. And note that you get an output which basically says you have fitted the data using random forest classifier with these default set of values. Okay, so these are the different parameters, and if you want, you can go and tinker with any of these parameters, but for this video we will not do that. We will just use the basic set of parameters that random forest classifier gives us. And once you fit the model, you need to go and predict the response values. So what I will do is I will use the same variable CLF and say predict X. So it will give a list of Y values for each of the X values. Okay. So for example, if there are 10 observations, the X matrix will have 10 rows and Y pred will have 10 different values, but each will be of one dimension. Now that we have the Y predicted values, what we need to do is how our machine learning algorithm has predicted, like has it predicted the values the way they are? Has it really predicted a Setosa species as a Setosa, something like that? So what you need to do is you need to calculate some kind of a metric, some kind of an accuracy score. So for that, first I will go and import metrics from sklearn, and then within metrics I have this particular function called accuracy underscore score, where you will pass both the Y and the Y pred, and note that Y is the actual values and Y pred are your estimated values. So if you give both Y and Y pred, it will compare the values within Y and Y pred, and basically it will tell what percentage of Y values are matching with Y pred values. And note that we are getting an accuracy score of 1, which means that all our predictions are absolutely correct. Our machine learning algorithm has done a terrific job of learning the relationship between the data. Now, instead of random forest classifier, what I can do is I can go and do the same thing with another classification algorithm called a logistic regression. Okay, so anyway, we will not go into details about how the logistic regression works, but we will just import it and just see how logistic regression performs, and pretty much execute all of the different statements, and note that I get an accuracy score of 96%, which is not really bad, but probably not as good as your random forest classifier. Training and testing the model on the same data provides us what is known as a training accuracy. Note that the goal of any machine learning model is to estimate likely performance of a model on out of sample data. But if you are using training accuracy and if you are trying to maximize the training accuracy, it rewards overly complex models that won't necessarily generalize to new data that may see in the future. And having a overly complex model will unnecessarily overfit the data, and such a method or such an evaluation method can never be used in a production setting. So we will move on to the next evaluation procedure, which is the train test split. The train test split is an improvement upon the previous method where you split the data into two pieces. The first one is the training set and the second one is the testing set. Here we train the model on the training set and test the model on the testing set and evaluate how well we did. You can split your data however you want. This is just a rough figure. You can split it either by 60 to 40 or 70 to 30, any way you want, and that really does not matter. So I will go to my Jupyter notebook and see an example of how to split the data into training and test sets and how to do the evaluation. First, let me import the train test split module. So the train test split module is available within model selection. So I will use sklearn dot model underscore selection import train test split. Train underscore test underscore split, and let me execute that. To split the data, you need to use the function train test split. So I will say train underscore test underscore split, and within the function we need to pass in the x and the y, and x is a feature matrix and the y is a response variable. Okay, and then you need to say what is the test size. Here you can say your test size as your 40% or your 30% or 20%. Okay, so just say the test size is nothing but 0.4. Okay, and we need to get the values which are coming out of this function and assign it to different training and testing variables. Okay, so the way we do that is we just say x underscore train, okay, x underscore test, y underscore train, and y underscore test. So what will happen is that since we have 150 different observations and 150 different values for x and 150 different values for y, it will split the entirety of the data into training and testing data. Okay, so the x train will have 90 observations and the x test will have the remaining 60 observations, and the same way the y train will have 90 observations and the y test will have remaining 60 observations. So let me execute this. And to show you how we have got the data, what I will do is I will execute the shape property. So I will say x underscore train dot shape, and you see that we have 90 different values. Okay, and these are the 4 different features. And if you say x underscore test dot shape, you will get the remaining 60. Okay, and if I say y underscore train dot shape, I will get the first 90 values, and if I say y underscore test dot shape, I will get the remaining 60 values. So now, having the data split into a training and a testing set, we just need to use the training set and train our data. Note that we already have initialized our variable CLF to a logistic regression. So I will use the same variable over here and train the new set of data. So I will say CLF dot fit, and I will try to fit only the training data. Okay, so I will say x underscore train and y underscore train. Okay, so now the CLF variable has been trained on the training data set. Okay, so it has learned the relationships of the data within the training data set. So now we will use that CLF variable to predict the values for the testing set. So I will say CLF dot predict. Note that this is the 4th step, fitting is the 3rd step, and the predicting is the 4th step. And I will say CLF dot predict x underscore test. So basically we need to predict the y values for the testing set of x. Okay, and I will store this into a variable called y underscore pred. This is called ypred because it is the prediction of the algorithm and it is not the actual values of the algorithm, or rather the actual values in the data set. So now I have y underscore pred. So I will use the same metrics module and the accuracy score. So I will say metrics dot accuracy score, and I will pass in both y test and y pred. Okay, and note that y test is coming from the initial data set, and y pred is the values that are being predicted by our algorithm. Okay, so let me execute that, and we are getting an accuracy of 97%. Using train test split produces what is known as a testing accuracy. Testing accuracy penalizes models that are too complex, and it overcomes the problem that we had with the earlier method, which is that of producing models that are completely overfitting. But the downside of a train test split is that it provides a very high variance estimate of out of sample accuracy. So let me go to my Jupyter notebook and explain you what do I mean by that. So note that now the accuracy is 97%, and this train test split method randomly allocates the observations into a training set or a testing set. So if I execute the method again and try to fit the data and get the predictions and calculate the accuracy score, you see that the accuracy has fallen down to 93%. So that's what I mean by saying that train test split produces what is known as a high variance estimate. The real estimate basically depends on which set of observations are there in the training set. So you cannot meaningfully rely on a train test split method to produce accurate results. So you might wonder, what if we created a bunch of train test splits, calculated the testing accuracy of each and averaged the results together? And that is the essence of the third method of evaluation, which is called the k-fold cross validation. So in k-fold cross validation, we split the dataset into k equal partitions or folds. The k value can be anything. Here I have taken the k value to be as 10. We use the fold 1 as the testing set and the union of the other folds as the training set, and then we calculate the testing accuracy. We repeat this step for 10 times or k times, each time calculating the accuracy score and averaging the accuracy score of all the 10 different instances. And the average testing accuracy is used as the estimate of out of sample accuracy. So first, let me import the cross-val score module from sklearn.crossvalidation, and I will go and execute the function cross-val score and store the output of that function in a variable called scores. This variable scores is an array and it holds the result of each of the 10 different iterations of a validation that we are going to do. Okay, so within the cross-val score, I need to pass in an estimator, which can be anything. It can be instantiated to either random classifier or logistic regression or KNN. And then I need to pass in my x and y values, and I need to say what are the different number of folds that my data set has to be divided into. Okay, so basically I was using 10 folds in the slides, so I will give a CV as 10, and then I need to score this for accuracy. Okay, so once I get the scores, what I can do is I can go ahead and print the scores. So if I say scores.mean, it will print out the average of the score of the 10 different iterations. So as you observe, the cross-validation makes a more efficient use of the data, which means that every observation is used for both training and testing the data set, and which means that more accurate estimate of out of sample accuracy when compared to the train test split method. In this video, we learnt about what is machine learning, and we have tried to understand how machine learning works with the help of a email classification example. And then we talked about the iris dataset, and in the machine learning process, we understood how important is to evaluate a model, because we may be generating different models for our training data, and there is a necessity that we choose the right model for our data. And we looked at the three different evaluation techniques, which are training and testing on the same data, train test split, and k-fold cross validation. And then we have made use of the Jupyter notebook to look at an example of each of the different evaluation techniques, and we have concluded that the k-fold cross validation is a much more supreme way of evaluating your methods. But that doesn't mean we should necessarily ditch the train test split method. Train test split method is used more often in the data science projects because of its simplicity and faster evaluation times. Thank you.